take us away on what is up with DDP.
Okay. Yeah. Hi. So for DDP tracing cases, people have been asking whether we can trace like a DDPs or reduce in the backward. And fortunately, now that we have compile autograd, and so we are thinking that can we use compile autograd to trace DDPs backward? So that's the motivation. So compile autograd does two things. First is it it replaces like the original autograph and create an FX graph and to represent the backward, and it also can represent a post hook. So that's what we need because we in the DDP we actually use post hook to fire some to check the gradient to see if the gradient are ready and if we need to do bucketing, if we need to do O reduce. So that's what we need to trace the DDP. But things got more complicated when we actually look into this issue, when we actually look into this task. So DDP's its reducer is written in C++. And all reduce are fired in the C++ label. So even though that compile autograd can actually trace this post hook, but it still cannot understand what's happened inside the post hook. So for compile autograd's original approach is using Dynamo to compile the post hook. So the post hook needed to be traceable by Dynamo. But again, like I mentioned, DDP's reducer, its post hook is written in C++ label, and it will decide whether it's going to fire or reduce or not. So if we simply wrap this post hook as an operator, Dynamo can only see, okay, there's one operator, but it cannot see whether this operator fire or reduce or not. So for this approach, we still cannot trace the or reduce. So another suggestion I got is we can actually write Python version of this post hook. But the post hook is pretty complicated, so we don't want to maintain two versions. Yeah, so I think Voss has a question.
Just for my ignorance, post hook is a hook. Is it a backwards hook?
Oh, sorry. It's like when the gradient is ready, the post hook for the variables post hook.
What's the mechanism that it uses? Is it like some custom mechanism? Is it a backwards hook? Is it something else?
For DDP, we actually register the post hook for gradient accumulator.
Voss, it's a backwards hook.
Okay.
There's a distinction between pre-hooks and post-hooks, which Chin-Chin
Yeah.
is making here.
Yeah, but I wasn't sure if it was some custom notion inside DDP or if it was just a hook on it.
It hooks into the regular autograd mechanisms.
Okay. So are we just going to get this for free when we solve backward hooks?
No, because as Chin-Chin was saying, it's written in C++. You can't dynamo through it.
Yeah.
Which part is written? The call to register it or the contents of it?
The contents.
Is it purely C or is there like a Python entry pointed to a C function?
It's purely C++ and it's unaware anything of Python.
I see. And what happens inside this hook? You call a collective, and what else do you do?
So basically, it traces like it check like whether we need to do bucketing, whether we need to do rebucketing, and then we'll fire the async or reduce, and later we will call wait. Yeah.
Got it.
Yeah. So the main problem we just described is we cannot trace it because it's in C++ level. So we can rewrite or like have another version. We cannot rewrite it. We can have another version of post hook, like written in Python. But we don't want to maintain two versions. So that's another solution, but we don't want to take it. So right now we are thinking to have the third one, which I have a draft PR to implement is instead of like actually doing the post hook currently implemented in DDP reducer, like what we just described, what does this post hook do? It just check the bucket to see if we are going to do rebucketing and if we are going to fire or reduce. So instead of doing this rebucketing or bucketing things, right now our solution is for each post hook, we just replace it with a Python post hook. But this post hook only does one thing for now, is to fire or reduce. Because each post hook represents a gradient is ready. So we just need to fire one or reduce for this gradient to gather the gradient. So this means that we are not doing any optimization if we compile with compile autograd and dynamo, but we actually trace all the or reduce, and this or reduce is functional or reduce. So later, what we can do is in the inductor level, we can do bucketing in the inductor level to fuse this or reduce. So basically, this is the solution we are trying. And right now we have a PR and we can trace the or reduce. So the next step is we want to try fusing all this or reduce in the inductor level and to see if we can measure the performance. Yeah.
I think I would add one thing, like it's not really clear that tracing the original DDP and then doing compiler optimizations is better than doing what Chin finally proposed, which is to trace a simple thing and then do optimizations. So I think it's likely we want to do compiler optimizations for communication. And it's also likely that we want to have those optimizations working on not just simple DDP case, but also cases like DDP plus like tensor parallel or something. And so there could, so in the end, I think like it could be directionally good to actually trace out the simpler form where we do one communication per parameter and then like doing the optimizations later.
This is sort of analogous to the per parameter sharding debate
Right.
with FSCP
Yeah.
as well.
Yeah. So I want to add some comparison here is if we actually trace the reducer's original post hook, then one downside of this approach is that suppose we can actually achieve this. In the inductor, if we want to do rebucketing, we actually need to figure out how to do a rebucketing. But if we trace the individual or reduce, then we simply need to do a fusion. So that's the benefit of this approach. But there is also downside of this, like our proposed solution is DDP also supports some customized communication hook. And it also has some default communication hook, meaning that when a reducer decides to fire an or reduce, it will call back to some Python communication hook, which implemented by user or some, like some default communication hook, like included in DDP. And this communication hook can do, for example, mixed precision, like a precision compression, a gradient compression. So this is slightly hard to support if we do per parameter or reduce tracing, because all this communication hook currently is written in the sense that all the or reduce are fused.
So in other words, if it were pointwise, then you probably could just run it every time. But if it like actually did something, I don't know.
Yeah, so
I don't even know.
I checked some implementation. So for some simple communication hook, for example, BF16 compression is just like convert the gradient to a BF16 and convert it back after or reduce. So this kind of communication hook we can support. We can basically just trace it using Dynamo. Then later we do in the inductor we can do some optimization. But for PowerS GD, it seems like it's pretty hard to support at this moment. Yeah.
Okay, any more questions? All right, this makes sense to me. Thank you for the clear presentation. Okay, moving on. So we can't move on to the next topic yet. So Animesh, you're here, right? Yeah, just tell us about what's going on with CSE guard trees.
Okay. So just a background on guards. So whenever Dynamo compiles a function, we have a check fn that runs before the frame, and this checkn has these guards, like whatever we specialized, whatever Dynamo specialized on, like some integer or the type of the object, we put these guards in this check function. And currently, what this check function is basically, you can think about like a Python string, where you have these different expressions and we add them together. Now this is slow because what's happening is we are gonna call C Python interpreter to run this Python string. And the goal of this project is to basically reduce the overhead of this check function. So for that, we are moving to C++. And the current proposal is to do two things. The first thing is to run fast, like basically move lot of these checks, maybe the most important checks to C++, and also fail fast. So what happens is, suppose you recompile, so you'll have multiple cache entries and each one will have a check function. And we run this check function to see, okay, is this the cache graph that we should use? If not, let's move to the next cache entry, run the check fn again. Oh, this is not. So we move in this way. So what we want is for the cache lookup to be fast. We want the check to fail as early as possible so that we can do quick lookups and find the right cache entry. So the goal of this thing is to do two things. First thing is to run happy case fast, where you always get a cache hit on the first entry. And the second is to make the fail case fast, where you have multiple cache entries and you fail sort of quickly on each cache entry until you find the right one. So the first one could be done by moving to C++. And for the second one, what we are doing is for each, like what we want to do is we want to basically somehow reshuffle the guards in a manner such that the guards which fail very frequently, they run first in this order. And currently we can't do that. Currently we have this string of Python function. We have a string of this Python that we run, and that is sort of static. So when we move, so like does the problem statement make sense? Any questions till now? Okay, good. So the way we are doing this is by creating a guard. It's like so we are creating a guard structure where earlier the guards were sort of this set and there was no relation between different guards, but now we are creating a guard tree structure. So there'll be a root node which will say, okay, like sort of if you think about f locals, like there's a f locals, there's a root that belongs to f locals, and it will say, okay, I have a guard on f locals foo or f locals bar, and then basically that node will contain the children guards. So like you will have maybe like bar.x or bar.y, and the x can be tensor, y can be integer. So we are basically creating this tree of guards, and at each level there will be a guard manager that is responsible for running the checks on that node object. So by creating this guard tree structure, we get CSE by default, because that since we are creating the check, since that node is responsible for running the checks on that node, we will not have to start from the root. Like we will not have to do flocals.foo.x. We will just do foo.x and foo.y, and then only we will go back to the sort of the root node.
Animesh, I'm going to interrupt you for a second. You don't happen to have any diagrams handy, do you?
No, I don't right now.
Okay.
No, everything is at tech. Yeah, I plan to write a doc though. Yeah. So and yeah, and at each node, so like at each node we have these children. So like you can think of each node has child sort of guard managers, and each guard manager is also keeping a count of how many times it failed. So basically at runtime there's a list of guard managers, and we basically iterate over that list, and each guard manager calls its children check functions. And since we are keeping a track of how many times each guard manager failed, we can reshuffle, we can sort the guard managers whenever there's a guard failure. So that the next time when you run the check function, we run that guard manager which failed most frequently. So in this way, we sort of move, we make the second case, which is unhappy case, fast by running the guards which have high fail count first.
Okay, so I want to make two comments, and then I want to ask Voz for questions. So the two comments I want to make is, one, in the past we've talked about a thing called guard trees, which is different from this. So what Animesh is proposing is to set up a tree structure on each check fund individually. So there's no sharing of the trees between check funds. All you're doing is just making sure you aren't recomputing the same source over and over again when you're in some deeply nested situation. And so he's solving the how do I run it fast when there's lots of cache entries with the reordering thing. The second thing that I'll point out is that actually no, that's what I want to point out. Voz, you were the one asking questions on the PR. Do you have any quick questions here?
Yeah, I think you can sort of break this down into three implementations that all vaguely solve the same problem, and I think we'll have to do all three. One is guard trees, which are trees that span all the cache entries, right? And then the thesis there is that if you could imagine that you have multiple cache entries for the same frame, and there's a lot of overlap because not a lot has changed, then next time you go to evaluate that frame, imagine you have k entries, but the first entry should just be the delta of what's changed off of the first one. So if you have, I don't know, 50 guards, and then you run those, you detect a change because some integer was 5 and now it's 6, you should pull that guard out. And then the next time you run, you'll have a frame cached at the whole battery of guards plus a leaf node of 5 or a leaf node of 6. And then the idea is your tree spans the entire cache entry structure, and you only ever run each guard once, regardless of how many frames you accumulate. This will also let us get rid of the cache size, because once you've run the initial overlap of all the guards, maybe there might be 2 or 3 entries, but once you've run the overlap of guards, each subsequent entry in the cache tree should just be the size of 1 guard, most, maybe 2 or something like that if we get fancy. But one that's the sort of thesis there. That's for guard trees. The priority queue thing, which is what Animesh is hinting at, is like, okay, we sort of hand wave away managing guard relationships, because we do have those, right? You can't access some value at attribute foo if you didn't do a